Welcome to my new calculus channel. My name is John Gabriel and I'm on a roll, so I'm going to discuss the last of the 5 requirements or claims, as they are called in Greek, aitήματα, in the Elements of Euclid. And so if you recall, I discussed the derivation of the first 4 requirements from nothing. The straight line, which comes from the definition of a point, the extended line, which comes from extending a straight line, and the circle, which is generated by a straight line. And finally, I arrived at right angles by showing you how to derive all those concepts systematically. So I'm going to do a little bit of revision and then show you in a moment what the meaning is of requirement 5. Requirement 5, which is the so-called parallel postulate. It's a misnomer, by the way. It's got nothing to do with parallel lines. And I'm going to explain to you what that's all about. And this will be the final with respect to the 5 requirements. So let's begin. Now, you'll recall this was the video in which I started defining the different parts of a circle. Remember, you have to define everything based on the previous requirement. You can't just suddenly out of the blue make a definition that has no basis whatsoever. So now, in this video, I'm going to show you why these things that I've been explaining to you are true. So I told you there are no axioms or postulates in mathematics. Okay, and these requirements are all well defined, and I showed you the straight line, that it is really just a path between any 2 points, the shortest path, and that there are many other paths, by the way, between these 2 points. I could have a path going like this, and another one going like, well, I didn't mean to do that, like that, all the way around, and there are an innumerable number of paths between 2 points. Then I showed you how you could extend the straight line, and actually the very proof of this is that if you take a shorter section, a shorter distance of the straight line, the proof is concluded, because obviously these red parts here are the extensions, aren't they? And finally, I gave you the definition of a circle, which is just the path created by a straight line between a center and all the locations on the path. Now, how is this possible? Well, you could just say that a circle is that path from which all the locations have the same distance to a given center, as you see over here. Okay? So that's pretty obvious, pretty easy, and that's how you generate a circle. And remember, in my book, I showed you that you have to also state that you can extend this line to the other side, because otherwise you could get circles that don't even look remotely like this. Okay? They could be jagged or irregular, as long as they're on the surface of a sphere. And then finally, I showed you how to get to right angles. I defined, first of all, an angle. By the way, an angle without a circle doesn't make any sense whatsoever, because if you do one complete revolution of a circle, every angle here, every angle is unique in terms of this ratio. Okay, so every angle is unique in terms of this ratio. And you simply define an angle as the length of that blue arc. So any part of the path that is the circle is called an arc. And of course, the distance from the center, or the straight line, which is the distance from the center, is called the radius. Right? So now we know that by symmetry, we can divide the circle in 2, right? There is no possibility of refuting that claim. Since the circle is symmetrical, all the points lie at an equal distance. If we take a diameter, right? If we take a diameter on the circle, like we see here, any diameter, it's going to cut the circle in half, right? Or in 2 equal parts. In other words, by symmetry, these parts will be equal. By the way, the idea of symmetry was stated in one of the notions of Euclid, where it says things that are equal to the same thing are equal. So this semicircle, this semicircle is equal to the semicircle because they are the same thing, okay? And you could easily take this semicircle and transfer it to this side because it's exactly the same distance from the center, right? So we know that we can divide the circle into 2 halves, and likewise we know that if we only have half a circle like that, if we take this radius or diameter here, it will divide the semicircle also into 2 symmetrical parts, okay? And so hence, by the property of symmetry, we know that 2 perpendicular diameters, in other words, diameters which divide the circle into 4 equal arcs, must have equal angles, and we call these angles right angles, okay? So that's how we get the definition of a right angle. And there is not even a need to prove that all right angles are equal because it's proved here. There's nothing further to prove. If you have any angle, you have to bring its vertex to the center, as I've explained to you. The vertex is just that point where 2 lines intersect, and then you have to see whether it's a right angle or not, right? So naturally, when we get an angle that is subtended on this arc and also on this arc and this arc and this arc, it's got to be equal, right? So, and then finally, we say that in a circumstance such as this, where the arcs are all equal, these angles are called right angles, or 90 degrees, or pi over 2. And so I have shown you now in a little bit of revision of the previous video. And now I'm going to talk about the last requirement. It says the sum of interior angles on either side of a transversal is constant. Okay, it doesn't say anything else. If the lines are parallel, then we are done, since we know that the cointerior angles have a sum of 2 right angles. Okay, and that, by the way, can be proved. And in this video here, using this diagram here, you can see, by the way, that if you take the sum of any 2 angles on the side of a transversal, they will always be constant, okay? As long as these lines cross, it doesn't matter, right? It doesn't matter. And what it means is you can move this line any way you like. Watch this figure up here. It doesn't change, okay? It doesn't change. It will always be this value, okay? There's no change. That's what the theorem says. So if the lines are not parallel, then we know their triangle is found on the side of the transversal where they meet. And the proof of these things is found in my ebook in the chapter which says there are no axioms or postulates in mathematics. So if I had $1 for every mainstream fool who voiced his stupid ideas, I'd be a very, very wealthy man. I mean, you look at idiots like Professor Raymond Flood with his YouTube videos. He's a total moron, knows nothing about Euclid's elements, doesn't understand them, and he's not the only one, by the way. No one after Euclid and before me understood what Euclid was attempting to do. Not even Sir Thomas Heath, who translated the elements. No one, and I mean absolutely no one before me and after Euclid understood that these requirements are derivable from nothing. The ancient Greeks, of course, had no problem with this. They all understood that these were derivable from a void universe. In other words, right from the beginning. They didn't believe in axioms or postulates. The word atimata in the Greek is incorrectly translated as postulates or axioms by Thomas Heath. It doesn't mean axiom. In fact, the word axiom doesn't appear anywhere in the 13 books of the elements. I bet you didn't know that. Also, the word that is used at the beginning, itisto, doesn't mean I postulate or let it be postulated as Euclid claims. It doesn't mean that at all. It means I require or I need the following to be understood or in place. And because it wasn't a problem for the Greeks to do it, Euclid didn't bother writing these things down. But every Greek mathematician knew that these things could be derived. So finally now, if you claim that these are axioms, you're actually elevating the ancient Greeks to God status, okay? In other words, they're like gods because nobody before or after them was able to realize these concepts. But the truth is, this is the truth. If they hadn't realized this perfect geometry, eventually some other human race would have. Because perfect concepts exist independently of the human mind. If an alien has to think of pi, he'll think of it in exactly the same way as we think of it. In other words, the attempted measure of a circle's periphery using its diameter as unit. Okay? So I hope you've learned a lot from these things. Please click like and become a subscriber if you're not one already, and share the news. And remember, there are no axioms or postulates in sound mathematics, especially in the geometry of the ancient Greeks, which is beyond refutation. And one final thing I'd like to address is that, when we talk about parallel lines, you cannot talk about them in any other context excepting in a plane. So some idiot who comes along and says, well, non-Euclidean geometry can have parallel lines. Those are not parallel lines. That is something else, okay? It's not parallel. So the infinitely many morons in mainstream academia have obfuscated everything in mathematics. They've turned it into a circus, which I call mathematics. Please download my free ebook, study it, because it contains a definition of the new calculus, which doesn't contain limits or nonsense like infinity or infinitesimals and all that other BS. Very well. This is the New Calculus channel, and I'm John Gabriel. Goodbye.